Okay, so our next speaker is Alex Best from Harmonic that is going to present a talk entitled So Computers Can Prove Theorems in Lean. What next?
Okay, does this look good to everyone? Yeah, you can read it, right? Cool. Okay, yeah, thanks very much for the invitation, the introduction. It's great to be here. Yeah, I wanted to give this talk because I feel like we reached kind of an interesting point in sort of formalization, and this is something that I think, at least personally, I've kind of been working towards for a long time, and it sort of feels to me like it's sort of finally happening. But I'm very much working for one of these AI companies, so I'm kind of bought into the hype. So I would love to be challenged if you really think that this is going too far. But I feel personally that we reached a point where, yeah, computers can prove theorems, right? They can do things that we, up until a few years ago, would have thought were maybe slightly ridiculous, kind of autonomously. I'll give plenty of examples, don't worry. Perform tasks that we previously would never have expected computers to have the capacity to do. And yeah, I want to talk a bit about that, about how those systems work, etc. But I want to also think a bit about like what's next. How does sort of doing formal mathematics change? How does contributing to MATLAB change? What does this new world look like when suddenly you have this sort of co-author who works very hard and works when you sleep? So that's the idea of the talk. So yeah, computers can prove non-trivial theorems in systems like Lean. I think that's clear by now. And recent AI systems, such as the one that the company I'm working for has built, called Aristotle, can autonomously prove sort of many thousand line formal proofs in a reasonable amount of time, right? This is no longer sort of a thing that's sort of unattainable. We have an API that users can use. There'll be a session later where people can try it out. And it will give you a multi-thousand line proof within a couple of hours for many people at once. These things kind of have reached that scale. And yeah, I want to think a bit about how our workflow should change and which parts we still want sort of human input for, and which new projects should we take on. I think this is maybe the biggest thing I think we should think about is where can we go next, right? Now we have a new tool, we have a big hammer. What are all the nails that previously we never would have considered possible? And yeah, finally, sort of like, how do we integrate all this stuff into MATLAB? I think maybe there are some MATLAB maintainers in the audience, and maybe some of them despair at the idea of sort of AI-generated code coming in like a flood. I mean, maybe this is similar to Leo's issues with users, and you don't want to be overwhelmed. And I guess we need technical solutions there, right? We need ways of ensuring quality that go beyond kind of human review. So what sort of theorems can computers prove? Well, it's true that computers have been able to prove theorems for a long time in a sense. So the first example, I'm not sure if we actually saw it already, is simple tactics, right? These are tactics that apply a single kind of bespoke, kind of well-known algorithm. So in the case of linarith, this is a tactic that does sort of linear arithmetic, right? So it can solve, kind of like matrix equations essentially, and it's highly reliable, but it's sort of narrow in scope, right? So it has a job, it does its job very well, but the second you kind of go outside of that domain, it kind of falls apart. Nevertheless, it's very, very useful. I didn't put it on the slide, but at some point I looked at like what the most complicated linarith proof in MATLAB is, and I could not understand it, right? So you're in the middle of a file where you're working a complex manifold and you have 500 hypotheses floating around, and there's some inequalities about x1 and y1, and linarith just does it for you, right? It sort of doesn't care that there's a lot of things in context. And so even this simple tool can produce sort of a proof that I would say no human ever sort of thought about. It didn't pass through the human's head. They just reached a point in their goal where they thought, oh, this looks like something linarith can do, and they typed linarith and it did it. So it's true that computers have been able to sort of autonomously, in a sense, prove theorems for some time, but that's sort of not the most exciting thing. So, well, we just heard about Grime. These are kind of the next step up. So these are more powerful automations that sort of combine things like linarith, and they combine other existing tactics, and they're sort of fundamentally handwritten in the sense that they are created as a hand-designed procedure and then kind of tuned by adding these little attributes and kind of tweaking priorities and parameters and this sort of thing to get something that's performant. So even though no one maybe sat down and wrote, what the algorithm should do in every case, it's sort of user extensible. They are fundamentally kind of driven by humans, right? A human has to go and say like, okay, this looks like a good grind lemma. Let me tag it. Now grind got a little bit more powerful, et cetera, et cetera, et cetera. So these are a lot more useful. I think Leo has a showcase of like things that grind can do, and it's really quite impressive. Especially in fields like software verification, you can really, solve sort of entire problems just by typing grind, right? So that's already a theorem, or a sort of theorem that human can prove. And then the next stage is these AI systems, right? So how are these different from the above? Well, generally they're sort of models that do some sort of search for proofs. So in that sense, they're similar to grind, right? They're doing search. But the difference is that they learn in a very unstructured way, right? They don't learn by someone tagging new lemmas or implementing new procedures. They just learn by kind of like throwing in data and trying to fit a function. So this means they can be kind of trained on internet data, on very unstructured data, and you rely on sort of the sort of principles of machine learning to teach the model, right? And this makes them a lot more flexible. It makes them generalize a lot better generally, because they aren't so reliant on specific tagging rules or specific implementations, and it lets them kind of generalize from informal mathematics a lot better. So yeah, they're more flexible, but I think maybe one key point is that they still use the above as building blocks, right? So this isn't sort of replacements in these cases. It's like you have some basic tools, and then you have a higher level tool, and you have a higher level tool on top that uses the previous two, right? So all these things kind of work in concert now to prove complicated theorems. So what are some complicated theorems? There are users of systems like Aristotle using it to obtain novel proofs and to auto-formalize existing arguments. And I would say that the boundary between these two things is a lot more blurry than it first appears, right? If you're given an informal argument, it has a gap, and the AI fills in the gap, was it a new proof? Was it an old argument? I think in reality, these things are not clear-cut, and we shouldn't kind of treat them as clear-cut. So there's this website called Erdos Problems, which attempting to collect at least every problem that Erdos ever asked. Now, Erdos was extremely prolific. That's why this website is interesting. And it has over 1,000 problems. And of course, some of them are incredibly hard and may never be solved. And some of them are solvable. And some of them are even solvable by AI, right? So this is an example from Boris Alexeyev, who I think is here, where one of these Erdos problems that previously no one knew of a proof, fed it to Aristotle, and it came up with a proof, right? So this is an AI-generated proof that, as far as we know, didn't previously exist. And once again, I would say I don't want to be kind of so like purist about like, did this thing exist in some form or some other form? The point is, this is a useful tool for creating arguments. So we can use these tools to sort of check the output of informal models, right? We're doing formalization. We have guarantees of correctness. And so you can take sort of an argument from a human or from some LLM like ChatGPT and auto-formalize them and kind of correct them as needed. And they've also been used to kind of auto-formalize people's papers in real time. So this is Bartosz Nastrecki, who had a problem that I think he came up with while playing some sort of like board game, and generalized it to some complicated statement in group theory about certain subgroups of the symmetric group and being generated by certain relations. And once again, fed it to Aristotle and came up with a proof. So, these are quite non-trivial at this point, is the point, right? I think if I'd given this talk 6 months ago, I would have showed you some examples, and they would have been maybe significantly less interesting than these two, right? So that's the point we've reached. One thing I'd like to point out here, and maybe it's a bit small, I can read it. It's this line is over 2,000 lines long, right? And you might say, well, maybe this AI is just really, really bad at lean, and like maybe it wrote 2,000 nonsense lines. I assure you, in this case, this is not the case, right? Like this proof is genuinely quite tricky and requires, at least 1,000 lines, let's say. Right? So we're at the stage where you can take some sort of argument that you've kind of vaguely sketched out and kind of feed it into an AI and get a formal artifact. So people use this for filling out libraries. So MathLib, of course, is the library that a lot of people here are interested in filling out, but there are many others now. And one I'd call out here is the lean quantum information theory project, which attempted to sort of, let's say, clarify the informal literature, where there were several papers written that kind of contained various arguments attempting to prove the generalized quantum Stein lemma. And it sort of wasn't really clear which was correct and which was wrong. Sort of every couple of years, a new paper would come out that was sort of correcting the old ones. And now we have a formal proof of one of them, right? And part of that formal proof was done by AI. And the final one is of course, IMO problems. I think someone mentioned earlier, like we entered our system in the IMO and it got a sort of a gold medal performance, right? So this is a kind of evidence that these systems can kind of generate quite tricky novel arguments on the fly. So I would say the most interesting thing to me about all of these examples isn't the fact that they're possible. It's the fact that all of them, apart from the last one, were done by sort of regular users from the lean and math community. Right? These were just done by people who signed up on that link and just tried out their favorite problem, or they tried out the thing they were currently working on. So this is kind of reached the point where it's sort of usable by regular people and not people who work for AI companies. And I think that's probably the most exciting thing personally. It's that this technology has like left the containment of startups and has kind of reached the point where normal people can just start playing with it. So I'm very excited for that, and I hope some of you will try it out. So please throw in your favorite theorems, your favorite conjectures, your favorite slightly easier variants of conjectures maybe, both formally, both informally, and just see what happens. They might get proved, they might get disproved. I think one thing we've seen a lot with some of these Erdos problems and other conjectures is that it's quite tricky to formalize things properly. And one thing these AIs are really good at is finding edge cases and bugs in your formalization. And this is going to save you some time either way. So I think it's very easy to ask a question these days, and you might learn something interesting either way. So I put some links there at the bottom for these references, and you might be interested in these sort of like user experience reports. And I think, like I said before, the thing which is maybe most interesting is that the way that these stories have gone is more collaborative than you might expect, right? The human asks a question, an AI gives an answer, a human read something in the answer that reminds them of something else. They look up a paper, they find some, it's really a dialogue. It's not so, so simple. It's kind of like ask a question, get an answer, solve a problem. There's kind of real knowledge being transferred from machines to humans and back again. And that's, I think, quite fun. So what changed? Well, I already mentioned this a little bit on the sort of the first slide, but for many, many years, there was progress from carefully engineered automation. So people thinking really hard about algorithms for mathematics, taking inspiration from SAT and SNT solvers, and kind of building automation in Lean kind of based on those things. And search was present, but it was kind of heavily constrained and tuned by hand. And these recent systems, they use machine learning based models instead to kind of basically essentially do the tuning without having to guide it by hand. And so what happens is that you're still doing search, but you kind of, the thing that suggests the next move is now a kind of a neural network, right? It's no longer a list of rules and maybe priorities, or maybe things which are tagged, or maybe things which are matched using a discrimination tree. They're just some weights of some neural network that make suggestions. And it has a lot of mathematics kind of baked in. And the main driver of progress here over the past year, 2 years, has really been reinforcement learning. So I'm not going to assume that people here are like experts on machine learning. And I think I should have said this at the start, but please like interrupt if you have questions. I'm very open to that. So this is something which works very well with Lean. So this is a process of training machine learning models where the models try something, and when they do good, you reward them and you tell them do more of that. And when they do bad, you punish them, or at the very least, you tell them don't do any more of that. And so this is a way of training models that is not training them to maybe imitate text on the internet, but training them to do well at a specific well-defined task. So this is great for Lean because Lean is a very well-defined task. There is a well-defined goal, which is to, for example, fill in this sorry and don't use any axioms, right? And don't do any other weird things along the way. And that's a goal that as soon as you define it, you can start training machine learning systems to achieve. So instead of training on kind of fixed examples of input and output and maybe getting a lot of humans to provide you training data, you simply train it to maximize the reward, which in this case is, well, we would use Lean, but there are others. So yeah, there are a few different rewards you could use, right? You could train a model based on numerical answers, right? You could have a list of problems where the answers are numbers, and you can train models by rewarding them if they get the right answer, or at least some answer that you can check. You could train them by telling them that they should write code that compiles and produces the right output. You could train them by telling them that they have to convince another model, which is maybe given like a rubric or some sort of grading scheme. So these are all things that people do to train machine learning models for proof. And the final one is the thing that we're doing the most of. It's producing Lean proofs that solve the goal, right? So you give a setup of a Lean problem and you ask the model, okay, run some search, and when you prove it, do more of it. So this kind of turns theorem proving into a game, and I think people who followed machine learning over the past few years know that games are sort of an incredible testing ground. There's been a lot of progress there, and as soon as you have something that feels a bit like a game, it's probably high time to really push it really far. So that's sort of the general picture. I want to spend a few minutes, because I think people hopefully will find it interesting, to talk about how the Aristotle system works. Specifically the system that we ran during the IMO, which is a few months old at this point, and we've made some changes since then, but I think this will still be big picture correct and hopefully interesting for people who've not looked at this sort of thing before. So the idea of the system is to kind of sit partway between sort of natural language mathematics and formal mathematics. So not to work only in a formal setting where you only produce tactics, but also to think informally sometimes and to produce comments that guide the search and to think, I think what we realized is that some things are formal and some things are not formal, right? You want to be able to do a bit of scratchpad thinking where you don't have to sort of justify every single derivation, and then use that to inform what your next formal step is going to be. So that's the kind of key here. And even though you're doing sort of a mixture of informal reasoning and formal reasoning, you're still interacting with Lean at the end of the day. And so you are still getting a precise feedback about correctness, about error messages, about what the new goals are after each state. And so this is a kind of a mixture of kind of, the purely formal and the informal setting. And I think it gives you kind of the best of both worlds. So there are some details in this paper. There's an archive link there, but I'm going to talk about the content of the paper for the next 10 minutes or so. So in this system, there are two main subsystems. And the first is a kind of a Lean proof search system, which is a Monte Carlo graph search, which you could think of it as similar to something that you might use in a chess playing agent or a Go playing agent, right? It's something that will suggest moves and then search over the consequences of those moves and suggest more moves, evaluate positions, right? In chess or in Go, etc. You would have an idea of, okay, well, I'm doing very badly because I've lost my queen, and you would ascribe some numerical value to that, and you would use that numerical value to kind of guide your search. So this is exactly the same sort of thing, but applied to Lean states. I'll explain a little bit more how in a moment. And that's kind of the core of the system. And the second is a kind of a lemma-based system, which is kind of higher level. So this is a separate system that suggests, ideas for lemmas or ideas for potential very high level arguments, and uses the subsystem, the kind of game playing type system to validate which ones are correct, and to use that to guide a kind of a higher level search that might feel a bit more like a search a human might think of, right? Humans, when we solve problems, we tend not to do a massively parallel branching search. We tend to try something, backtrack, learn from our previous attempts in a kind of a more linear fashion. So that's kind of the difference between these two systems. And kind of, yeah, the kind of technical difference is that, one of them fills in sorries and the other one proposes sorries, right? That's maybe a good way to say it. And so, yeah, we count a problem as complete only if we produce a lean kernel check proof with no gaps and no uses of weird axioms. So how does the proof search look? Well, I said it's kind of like a game. Mathematics is a bit of a strange game in some ways. There are a few ways to interpret it as a game, but I think none of them really capture what's going on very well. So here's an example of kind of a simple kind of tactics for proof, where we're trying to prove that P and Q or R implies P and Q or P and R, okay? And so, the lean aficionados in the audience will of course know by heart that this is what you do on the left-hand side. But let's say we didn't know how to produce this thing on the left in one shot. Well, we would know some kind of rules, right? Like, oh, whenever you have an implication, you want to use intros, right? That was probably in Barvik's table of useful tactics. And so that's a move you can think of in this kind of game of mathematics that takes this state where the goal is to prove an implication and transfers it to this state where you have some hypotheses and the goal is no longer to prove an implication, it's instead to just prove the conclusion, right? And okay, I actually have a slightly more complicated thing here, which is in addition, breaking down the and statement. It's kind of doing it all in one go. But the key point here is that, this is a block of lean code here, which has a sorry in, and that sorry kind of represents sort of the evolution of the game, right? That's the thing that you have to do next if you want to continue playing the game. And so in this case, there's kind of one move that you do, but you can imagine there being other possibilities, right? Maybe you don't know about intro, right? Maybe your first thought is, I should use grind for this. And then you'd probably win immediately, but it wouldn't make a very good demo. So we don't do that. And so we kind of continue. What happens next is quite interesting though, because we're trying to prove we have an or statement. And when you have an or statement, what we quite often want to do is to branch into two cases, one where the left-hand side is true and one where the right-hand side is true. And so in this kind of like game of mathematics, something kind of interesting happens in that you split one state into two states, and now you have to prove both of them in order to proceed. So this is maybe a bit different to a game like chess, where you never kind of split the board into two and have to carry on playing two separate games, right? But at least in this interpretation of doing mathematics in lean, this is exactly what happens. And so this is kind of how you can imagine the proof finishing at the bottom there. So the point I'm trying to make here, I'll describe on the next slide, but we kind of start with a lean block of code containing sorries, and we have sort of lean proof states, which are the goals and the local context, the hypotheses and etc. As the kind of the states in the search tree. And when we have independent goals, we split these states into kind of separate nodes in the search. The actions then, in chess, this might be making a move, are snippets of lean code, right? These are tactics, maybe with some comments, maybe not. And these apply to the state and produce new states, okay? So you have a tree where you can think, the states are the nodes and the edges are the tactics. And so as I kind of described it, it's technically like a hyper tree because sometimes you run an action and you get multiple states out, but that's fine. And so when we do cases, we branch. And so we have an interesting kind of logical structure on this tree where there are some states where we have to prove all of them to prove the parent. And whenever we have multiple tactics coming out of a state, we can use any of them to proceed. So that's the kind of the or in the structure. And another thing we do that I mentioned earlier is negation. It's very useful for these systems to be able to know when they've reached something that is impossible. So we also add to this structure the ability to negate a state and to try and prove the negation. So this allows the system to kind of cut off branches that are impossible. And so you have a kind of a slightly complicated structure. Yeah, so we have a complicated structure, but there is kind of very clear, well-defined logical rules about when something is proved based on when its children are proved or not proved, etc. So we can merge these states when they're have the same meaning. Maybe they differ by renaming or something, and so we don't kind of repeat work too often. And we can do the same thing for tactics. We can treat them as equivalent when they basically work the same. And this has the effect of turning the tree into a graph instead. And so we take a big neural network and we use that to predict which tactics to try next, and a value function, which is how provable we think the goal is. So how promising it is, right? And we use those to guide the search. So it's a parallel multicolor graph search, to use the technical words, which sort of focuses effort on sort of the hardest remaining sub-goals that are likely to help prove the theorem. It's a bit of a mouthful, but hopefully that makes sense. Yes?
What do you mean by where's the tree in the graph?
So yeah, imagine you were working on a proof and you reached essentially the same point in two different branches. Like maybe you did a case split or something and you needed the same side condition that F was measurable in two different cases. Then you would unify those and you wouldn't reprove it twice. Yeah, so there's, I kind of started this by saying that we were not doing hand-tuned search algorithms, but of course we have a massively hand-tuned search algorithm here, but so be it. At least the policy is a neural network in the value function. So, okay, so that's kind of the core search system. And so, yeah, for these kind of hard IMO problems, especially, also in the API if you use it, there's this kind of separate like informal pipeline that suggests lemmas and that sort of things and suggests informal proof sketches. And so the goal here is to work at more of this kind of like human-like high level reasoning level where, you come up with a reasonable strategy and maybe you don't quite know all the details yet, but you kind of at least know what the lemma should look like, and then you can kind of attempt to prove them. And if you can prove them all, it's going to fit together. And if you can't, then you probably need to try a different strategy. So that's the difference there. And so this has many stages, right? It has some auto-formalization, right? Turning of informal statements into formal ones. And we kind of apply this as kind of a big outer loop, if that makes sense. So this is a kind of a schematic, right? We take in the target theorem and we kind of try and come up with some informal proofs. We generate some lemmas, and then we kind of either try and prove and revise those lemmas using the search I just talked about. We can't prove a lemma, maybe there was a mistake. We can sort of try and recover from that. And we kind of do this in a loop. And in this way, can kind of take this search kind of graph-based algorithm and kind of apply it to problems that require a sort of a bit more kind of high-level structure from the start, if that makes sense. So yeah, I mentioned a bit that we sort of want to interleave formal and informal reasoning. So each of these proof steps, the model thinks informally and then outputs a step. So the model doesn't have to sort of like see a state and immediately respond. It can kind of do some preparatory work and kind of, I don't know, sketch out some ideas and then rank them itself and then decide which one is best, and then only then produce the tactic. So this makes the kind of tactics it produces kind of higher quality. And so it's kind of really more of a blend than it might appear between informal and formal reasoning. And yet we train them both together because it's highly likely that a good thought process leads to a good tactic, and a bad thought process leads to a bad tactic, if that makes sense. So yeah, these comments are sort of visible later in the proof, and that kind of helps the model kind of maintain a kind of coherent high-level strategy. Right? If you kind of work purely in a tree search kind of way, where you kind of can't see the history of what you did, it can be harder to kind of maintain this kind of coherent high-level strategy. And yeah, I think I kind of already said that, but we interact with Lean through this thing called the Lean REPL, right? The REPL is I can't even remember what REPL stands for. Right, read, execute, print, loop, or something. It's basically a way of kind of interacting with Lean, similar to how a human would, right? You're not just running the Lean program and passing in a whole file. You're allowed to kind of like make individual moves and get the response for each individual tactic and kind of work in a similar way to how a human does when they interact with Lean in the editor in VS Code. So this, we also find is a good way of interacting with Lean because it's really the way Lean is designed to be interacted with. You're meant to kind of work incrementally. It is an interactive proof assistant, and so using it as such, we find to be a good way to use it. Yeah, so this kind of outer loop, etc. Lets informal reasoning kind of explore ideas, but the formal verification kind of keeps everything grounded to only the sound ideas. Yeah, so how do we train this with sort of reinforcement learning? I think maybe it's hopefully becoming a little bit clear how this works, but you produce proofs, you attempt problems, and whenever you solve a problem, you reward the model for producing those proofs, and you say that sort of like the value of those nodes must have been very good because it turned out they were provable. So you essentially can just try a lot of problems and use the information from the ones that you solved to improve the model over time. So what you're kind of limited by is just lots of different problems to try. So you just need to get a lot of different problems and try them all out and keep training the model on new problems. And so, yeah, over time, the model kind of learns which kind of informal plans and tactics lead to short and kind of successful proofs, and it kind of gets better at easy proofs, and it can kind of, always close them out, and, you start to focus on harder and harder proofs over time, and the model kind of continues to improve. So that's the idea. So, yeah, at the IMO, as I mentioned, we produced formal solutions for 5 of the 6 problems, and it was crucial to kind of scale, to take a large model for that, to take many parallel lemma pipelines, and to take kind of multiple kind of iterations per problem. And in that system as well, we used a technique called test time training, which is where you don't just try the problem, you try the problem and then you train on the attempts that worked out well, and then you restart from the beginning, or maybe not from the beginning, from somewhere with the model that's been updated. So you kind of allow the attempts to be internalized into the model and let it kind of learn on the fly from these different attempts. And so this kind of lets the model specialize to kind of individual problems that it hasn't seen before a lot better, because it can kind of learn from different parts of the search graph in a way that just isn't possible when you're kind of applying the same model across the graph. So that's kind of a description of Aristotle and kind of roughly how it works. I now want to kind of switch gears a bit. And talk a bit about kind of how these things kind of change our workflows, etc. So I think the old style of working in a proof assistant was kind of, you would maybe select some big goal, right? Some theorem that you wanted to prove. Maybe it's your favorite theorem, or maybe it's like the most approachable theorem from your favorite area of mathematics. Maybe you're following some notes or some paper. You might work backwards from kind of the big theorem and find what you need along the way, or you might kind of sketch out a rough outline and kind of work forwards. And you would kind of refactor and kind of improvise as you go. You would kind of maybe find the lemmas that you need along the way just by kind of trial and error, essentially. And I think this kind of made sense when humans were thinking, and sort of typing was in some sense a bit of a bottleneck, right? Like, interactive theorem provers, quite often you have to type more lines of code than you would expect initially to kind of convince the proof assistant that the thing is true. And so, at least in my experience, that was often kind of the bottleneck. You had kind of lots of time to think while you were typing, and kind of this iterative process, kind of with the human constantly in the loop, was how you essentially discovered the proof, if that makes sense. And so I would suggest that, if you're working with one of these kind of AIs as a coworker, a better pattern, right? I think this is what we should all be doing, right? You should spend some time, really thinking through the problem and designing the structure, right? So what the main statement you want to prove is, what the useful lemmas are, maybe describe the parts of the library that are missing, and that will need filling in. Well, I missed the key point here, which is that you should submit this to an AI to work on. But yeah, of course, you should spend your time designing the structure, and then you should send it off to some system, right? And then I think what's ultimately key is that you should move on to another project, right? I have many conversations with Pavik who tells me that he can't resist working on the same thing as the AI at the same time, and essentially racing it. And Pavik's quite quick, and so he sometimes wins. And
I usually win.
okay. And I think this is really not the way we should be using it. We should resist the temptation. I mean, formalizing things is very fun, but you can get a lot more done if you have like 5 goals and you send them all off, right? And then the results start coming back in, and you start revising and fixing things as needed, right? Maybe one of them comes back quickly because it turned out the lemma you suggested was false, and you fix that one, you send it off again, another one comes back, right? And I think in this way, we really can get a lot more done, and we can advance these libraries much faster when we can sort of like essentially be a little manager, right? You have your 5 coworkers who are working really hard, and you're working at this high level where you're kind of analyzing what went wrong when something does, and you're kind of revising your plans, and you're adding a bit more detail where needed, but you're not kind of running through and spelling everything out at the start. So I would suggest that people should experiment with this and try it out. So yeah, just think of yourself as managing a team of like hardworking collaborators who are willing to try pretty much anything, even if it seems too hard, and do the majority of the coding. And they might sometimes surprise you. Yes, Patrick?
Okay, so you talk about analyze what happened and revise and iterate step it if needed. As far as I know, with the current setup, if Aristotle fails to find a proof, it doesn't tell me any debugging information, essentially. So at that point, what am I meant to revise? What am I meant to iterate?
Yeah, so maybe I'll repeat the question for, I don't know if people can hear that, but the idea is that, in order to revise, you need some feedback. Currently, you get feedback when the thing you suggested was false. I think it's a great feature of us, and I think it's definitely something we should do to give more feedback when the thing was maybe true, but it was just too hard, or there was some sort of other obstruction. We can definitely do that. But yeah, I think negations is a really a key thing, especially if you give a lot of lemmas. You'll often find that one gets negated, right? That happens quite a lot. And depending on, I don't want to get too like specifically about Aristotle, but like, I want to be a bit high level here, but like, depending on the system you're using and the actual interaction mode, it may do things that you didn't ask for and tell you, hey, I did this, but I couldn't do the main thing because, you made a partial def, and partial def, you can't prove anything, or something like that, right? Yeah, and so I think one key point here is that these collaborators, they're only going to get better over time, and so sort of learning how to effectively wield them is really a long-term investment at this point. I don't know why they would stop getting good now, and so yeah, it makes sense to kind of think about switching to a workflow where you're more like a manager than anything else. So the other thing I'd like people to consider, yes.
You similarly expect them to get faster?
Yes, I expect them to get better and faster. And
then you don't necessarily have to get into this workflow of waiting.
Maybe. I think as things get faster, people tend to demand more from them. And I think people just put longer horizon tasks, and you want it to come back to you when it gets stuck. And you probably do want it to get stuck eventually, because then otherwise you're maybe not asking it a hard enough thing. So yeah, I think there's definitely a big space of like possibilities here. Yeah. So yeah, I think the other thing I think is very interesting is like, previously there are like lots of interesting things that people just wouldn't find the time to work on. I mean, MATLAB is mostly curiosity driven, but I think people have some idea of, a project being useful and kind of having a cohesive kind of big picture strategy. And so I think there are a lot of these like really nice, beautiful pieces of mathematics that we can now sort of like incorporate into these libraries and formalize that, maybe they're not the thing that you were already working on, right? They were just like some fun thing that you see and you think, oh, it would be cool to see a formalization of that. And so I think we should cast on out sort of wider as well as deeper, if that makes sense, and kind of start incorporating all these fun things. So yeah, when the effort required kind of goes to zero, then you can get all these little gems and just kind of get formal versions of them and kind of look at them and enjoy them. So I would say we shouldn't think of only kind of speeding up our existing plans, but we should kind of expand the space of projects that we try and work on. And yeah, we should be ambitious, I guess, is my point, like about what we want these libraries to contain. And we shouldn't think too much about the way that, I think a lot of decisions are kind of made with a paradigm of kind of, okay, how long will it take a human to do this? And I think when you release yourself from that, there's a lot more that we can add. So this is the MATLAB growth over time. And I'm very sad to see that there is no significant uptick since the release of Aristotle. I would love there to be more. And what I hope is that it goes something like this, right? That's my dream. So like, what are the consequences of this, right? Right, if suddenly people start using AI and adding a lot of material to MATLAB, to other libraries, to Lean Core, if we start spamming Leo with PRs made by AI, I think nobody wants this to reach this kind of AI slop era, right? And I think we're in good hands because of formalization. Like, we do have this formal bedrock that means that we know that something isn't complete slop. But there are definitely kind of notions of quality beyond correctness, and I think that's sort of like the next sort of frontier for AI for formal mathematics, right? It's like we have a clear picture of how to improve correctness, but sort of these notions which are more humanistic, right? Notions of quality and style and reusability are not yet like well captured, and I think what we really need to do is kind of automate some of these things. So it's a bit weird for me to talk about this because this is something I was really interested in doing before I knew anything about AI. I just thought it was like a cool challenge to kind of automate the job of a MATLAB maintainer or a MATLAB reviewer and kind of add all of these, these linters and kind of find ways of reducing the human burden. Because even a few years ago, I had the feeling that MATLAB reviewer time was going to be a kind of a bottleneck, right? And so doing all these things automatically would be an improvement. And if anyone wants to talk this week about such projects, I'd be very happy to. Hi, Yanis.
I wrote a tool a bit like this for our internal use. Unfortunately, not open source yet. And I object to the characterization of intermediate project on the slide. I think it's actually very tricky.
You think it should be? I wanted to make it clear that this was not something for lean beginners to do this week. Advanced project maybe.
So my understanding is that Damian and Hester will talk about linting and also has at least one simple beginner suitable project to suggest.
That sounds great. Wonderful.
I'm not sure if he's here yet, but he will be there. So if you like linting, talk to him.
That is amazing. I'm very happy to hear that. Yeah. Okay. So yeah, I'd like to wrap up a bit by talking a little bit about like previous kind of waves of automation. I think one really obvious thing that people come to mind when you start telling them about formal proofs and AI proving things, and they tend to think about computers as calculators and this EDSAC machine and people doing big computations and maybe making conjectures based on that. And I think this is maybe not the best analogy. I think these tools, I mean, I'm a sort of a computational number theorist, so this story is like the key to my field existing. But these tools, while transformative in some ways, really only affected some areas of mathematics. And they also kind of rolled out very slowly, right? This machine here is sort of the size of a room. And yeah, it obviously came down over time, but this thing didn't have a kind of an immediate impact, I would say, in the way that most mathematicians work. And in fact, most mathematicians kind of work similarly kind of after things like this started happening as before. What I think had a bigger impact was sort of the internet and archive and sort of tech and this kind of redistribution of information, kind of the barrier for that being lowered, kind of split up communication, dissemination of ideas rapidly. And I hope we're at a kind of a similar point here where we have this tool that sort of every mathematician is going to use, and they're going to use it to like spread their ideas quicker and check their ideas quicker. And, you know, this shift from kind of hand kind of mimeograph notes to kind of nice typesetting. I hope we're kind of in a point of a similar shift now where we shift from kind of pure LaTeX kind of typesetting to having a kind of a formal version underneath and a nice AI that interfaces between them and kind of shows us what we want to read, but guarantees us the correctness. And I think that will speed up, you know, our communication, our dissemination of ideas. And I hope that this story is more similar, right? I don't want us to be in a world where there's a big machine somewhere that only 10 people have access to, and you know, they can do a cool thing, but no one else can. I really want us to be in this world. So yeah, I think I'm probably getting quite close to the end of time. So yeah, I put some questions here, and you know, how might the future of AI look? And I think people often think about chess here because there is a history of, you know, AI, you know, search algorithms getting good at chess and it getting kind of worse. For humans was sort of a big fear for a long time, and I think that hasn't panned out, which gives us some hope. Like people still enjoy chess, but what I kind of hope again is that we're sort of more like the Hubble telescope, where we have a big new thing that kind of helps us see much further and kind of do more science that was previously impossible than this kind of thing where we just automated a game that we enjoyed. So yeah, I'm really gonna wrap up there by saying what I've said already, which is like, take seriously the idea of working with an AI co-author for Lean and decide on some ambitious projects that you want to work on that you wouldn't have been able to before, and really think about, you know, which projects will suit this workflow, right? Which projects was the barrier that there was, you know, a lot of work that needed doing, not just that there was like one key definition that needed writing, right? I mean, if it's something like that, maybe you're better off doing it by hand. And so yeah, we should invest in infrastructure, more automated quality checks, tools to kind of manage these contributions, right? We have things like the blueprint already. I hope that Pietro will talk about Lean Architect, and I hope we'll have kind of more suitable tools kind of going forward to kind of interface with and manage these AIs. And yeah, I want us all to experiment a lot with new workflows, and I'm especially interested in, you know, people here this week who are like completely new to Lean. You're going to have maybe a very different experience to people who came to a workshop like this 1 year ago, where there was no way to kind of see what a correct proof of a thing looked like without going and finding someone. Now hopefully you can. So yeah, we should decide how we want the future to look. And yeah, I'm going to stop there. So thank you for your attention.
Okay, thank you very much, Alex. And we have time for, I would say, 3-4 questions. Oh, 5 maybe. So let's go. Yeah.
One question about the implementation of Aristotle. A typical problem is data generation, in the sense that there's not that much natural Lean data around, right? MATLAB is big, but in terms of AI, it's not that big. Mm-hmm. How did you address this? How did you get sufficient quantity of data?
Reinforcement learning, baby. It's just, you know, it's self-play, right? Like, yeah.
Okay, I see. And one very quick follow-up. So you talked a bit about kind of short, beautiful proofs, and that you optimize for these as well. What's the thinking behind that?
I'm not quite sure which thing I said that you're referring to, but
Like there was one sentence on one slide that said you, during reinforcement learning, you give rewards for short proofs. Is that correct?
Yeah, in some sense, yeah. Like I think, yeah, you want to encourage short proofs in some way. I think, yeah, one thing that makes Lean like kind of interesting as a game is that there's lots of moves that do nothing. And so, yeah, if you don't do something like this, you can often have bad performance. But
All right, thanks.
Hi, thanks for the talk. Is the action space limited to the MATLAB or actually statements that are already proven? What I mean by this, let's say I have some non-trivial result of mine, which I want to use in my proofs. Is it possible that the model, is the model going to use it without, is it possible to use it without retraining the entire system?
yeah, I think it depends a bit like how you would set it up. Like maybe depending what your result is, whether you would want to set it up as a sort of a hypothesis that this thing is true and kind of build from there.
Not hypothesis. Let's say it's already proven,
yeah.
And I want to use it as somewhere in my proof of the other statement.
Mm-hmm. And you have a formal proof already?
No, I'm the hypothetical question. Just is it possible to achieve this without actually retraining the entire system?
Yes. Yes.
And
sure.
how exactly?
So these models have context, right? So if you give them, you know, files with something in, they can look at it and they can build on it. And there is generalization normally between, you know, all the math they've seen before and all the new things that you have. So yeah.
So okay, my question. Okay, so the way the statements are tokenized, it's not just the Lean instructions, but also the natural language.
Yes. Yes.
And yes, that's a one related question. You also use, if I figured out, the comments in the proofs.
Mm-hmm.
Okay, that's it.
Yeah. This is sort of what I was trying to say with like sitting halfway between informal and formal. Like there's so much informal math out there, and you really want to use it. Yeah.
Hi, just wanted to say thank you first for the talk. I've had some really positive interactions with harmonic folks so far, so thanks. I wanted to ask about, you talked a bit about this kind of split and like different modes of how people write Lean, and this happens informally too. If like we talk about how, you know, for beginners it's a lot harder to write definitions, yes. And then even for propositions it's kind of subtle, right? Because the type of something in prop is very different from the proof itself in prop. So does this match up with the informal intuition that we have about, you know, like it seems it's very straightforward to think of the intuition of the RL stuff for things that are solidly in prop, but is this true that this is extremely harder for things that are in type, especially as you drift further away from established MATLAB?
Yeah, I think it's broadly true. I think the difference with prop and type, etc., is that if you make a bad definition, you have to deal with it for the rest of your life, right? Or until you change it, right? So you have this sort of like delay between, you know, I think a lot of people working on MATLAB could talk about this, right? Like you often formalize something and then you realize 6 months later, like, oh, I should have done it differently, right? And I think that sort of delayed feedback is tricky for humans, but also tricky for AI. So yeah.
Thank you.
Thanks for the talk. I have two questions, one for proofs and one for statements. When it comes to proofs, when you're leveraging the Lean feedback, what's your view between reinforcement learning of things like MCTS and direct inference with frontier models, for example, where you update a prompt and you simply do inference? And the second question is, how do you handle statements and definitions where you obviously don't have this feedback from Lean apart from syntax?
Yeah, so for the first question, I guess it's sort of, you know, we'll see. I don't have the answer there, I don't think, in terms of like, you know, what will be better in the end. I think, yeah, it's people will do experiments, and I think it will become clear at some point, like which thing works best. In terms of statements, yeah, you're right that there's not a direct feedback signal, but you could do things to get some gauge of quality, I guess. I guess I won't go into more detail there, but yes, it's true that there is it's not a formal notion of whether a formal statement corresponds to an informal statement, and so there has to be something informal there, put it that way.
Yeah, can you say some more about the large transformer that you're using? You said it serves both policy and value function, but can you just go more in detail about that?
I don't think I can go into too much more detail, but I can just say it's a large transformer that does policy and value, and yeah. If you have a specific question, I can tell you whether I can answer it or not. But
I think I just don't really understand like what's going on. So usually like transformers are used like the context in which I learned transformers to like predict the next word. Yeah, so I just don't really understand how you're like serving these policies and value function. Like, what are you inputting, outputting?
Yeah, the policy is just strings of lean comments and tactics, and so that is very much what a normal transformer will be doing. And the value is just a number, but a transformer can give you a number, the same as if we give you a token or something else. So does that answer the question? Okay.
Okay. Yeah, we have 5 more minutes, so like 2 questions or something.
Thank you very much for the talk. It's been very nice. I wanted to ask about the reinforcement learning model. You have like the very obvious reward function, that of the proofs being compiled and verified. But as you have said, there are many other things that are also desirable. For instance, the proof being, I don't know, maintainable with good style, good naming conventions, and so on. And I guess many of these things can be done like in a post-processing, but I don't know if you, if there are other things that are also taken into account in the reward function. I mean, to modulate like things that can be valuable in the first process. I mean, for instance, being general or the abstractions. Is the reward function in some sense modulated to take into account this, or is just this compilation?
Yeah, I guess I can't say specifically once again what we use, but like you could definitely imagine putting these kind of proxy rewards that measure other things that you care about in there, and kind of training for all of them simultaneously. I think that's reasonably, it's a good idea.
Okay, so we have the last question by Bavik.
Very nice talk. In your future view of what the lean world looks like and formalization world looks like, what's your vision of the importance of API design and definition choices? So at the moment, we have kind of MATLAB style conventions on the way definitions should look and the way good API looks. Do you think that will need to change? Do you think that should change? Do you think it could be relaxed in the future?
I think it's important that there is a core of things with sort of extremely good style that are reused between people. I guess I kind of imagine that is something like the archive, right? Where everything's kind of brushed up and it's polished and it's clean. And then everyone, when they're working on their stuff, they're free in their own little project to do whatever they care about, and to do it, fast and loose at the start, and then to clean it up. But yeah, I think in terms of scaling, like I wouldn't want a kind of completely, siloed thing where there's multiple independent formalizations of the same thing. I think there probably will be times when that happens and things need to be recombined, but hopefully some AI can do the recombination for us, and maybe that will make this problem a bit less severe than it is now. But yeah, I think we do want good style in the formal stuff, because I think we've seen many times how you get all these performance issues and other things when you do things wrong, and I don't think there's like a a way around that. Yeah.